Hey guys, it's week 3 of OS and here's the review. Sorry it's a little late, but as I'm sure all of you were today, I was a little bit busy with Project Zero. So, what did we learn in week 3? We learned about the different scheduling policies and the boot process, and we also learned about threads. Scheduling in the boot process. So CPU scheduling is really connected to the illusionist hat that the OS wears because it allows you to think there's more resources than there actually are because of the fairness that the scheduling policies allow for. So there's short-term scheduling and long-term scheduling. We're going to be talking more about short-term scheduling, but long-term scheduling is basically how many processes your OS is going to allow to try to run. This isn't implemented so much nowadays because you just give it your best try, but that is what long-term scheduling is if you run into it. Short-term scheduling is the scheduling of the processes inside the CPU. So short-term has non-preemptive schedulers and preemptive schedulers. Non-preemptive basically means that you're going to allow a process to run until it terminates. Preemptive scheduling means there's timer interrupts to interrupt a process in the middle of running so that other processes can run to give more fairness to the other processes. So how do we evaluate scheduling policies? There's 5 different criteria. CPU utilization, which is how much is the CPU actually being utilized when these processes are being run. The CPU isn't just idling because it's being blocked or anything like that. And then there's throughput, which is how many processes are terminated within a certain unit of time. There's turnaround time, which is how long it takes for the process to run. There's response time, which is how fast you can get user input to an output for the user. And then there's waiting time, which is how long a process is in the ready queue and not actually being run on the CPU. So what are the different scheduling policies? First, we have first come, first serve, or FIFO, first in, first out, which is non-preemptive. It allows for processes to run until they're terminated, first come, first serve. So if one process is scheduled, then another process, the first process will run until it's finished, and the second process will run until it's finished. Then there's round robin, which is preemptive first come, first serve. So you'll still have the queue of processes that came first and second. It's just you're going to give them a time limit to run. You're going to give them a time limit to run before you move on to the second process, and you're going to keep on doing that until all the processes have finished terminating. Then there's shortest job first. Shortest job first is ideal because you want to run the shortest job so that your CPU is getting the most throughput as possible. But this leads to starvation because if another process gets put into the ready queue that happens to be shorter than any processes that were already in the ready queue, it will be run before the other processes, which means that processes will end up not being run in a decent amount of time. It's also kind of hard to implement shortest job first because you have to use the past to predict the future, which we do a lot, but it isn't always trustworthy. Then there's multi-level feedback queues, which is actually what we end up talking about a lot, partly because they're more complicated, but also because they're a little more, they're used a little more than the other ones. So multi-level feedback queues have different queues of differing priorities. The highest priority queues are what's run first on the schedule. Like the scheduler runs those first on the CPU. It is important to remember that there are quantums, which is how long a process will get to run depending on the priority queue that it's in. It's also important to realize that whenever a process blocks, it moves up in priority. So That way, the I/O subsystem keeps busy. Okay, so that's the basis of scheduling in the boot process. Be sure to remember the different criteria because I'm sure they're going to ask about it. So remember those. If you come up with any mnemonic devices, please share them. And then threads. What is a thread? Threads, every process has at least one thread, which is the process that is currently running. More than one thread share the heap, the SDS, and the code. So they're always going to run the same code and they're going to have certain shared information. The shared information, the shared data, allows for communication between threads, which really holds a lot of power. Threads also give the illusion of infinite resources because they're just more things that can be run concurrently and give the illusion of more processes and more resources. So how do you use threads? Threads are created and managed with system calls just like processes. I believe there's something called pthreads, which is what it's mostly used with, which is POSIX compliant, and you're going to be using thread create. Threads are really cool because they model the real world and the concurrency that happens in the real world and shared things in the real world, as you saw with the too much milk example in class. And there's two different thread types. There's user level threads, which are not known. These threads aren't seen by the OS itself, so the scheduler doesn't know that this thread exists. So it's lumped in with the process that created that thread. So whenever it's getting scheduled, the threads aren't getting scheduled individually. It can, however, go into kernel mode if it calls a system call. It's just not a kernel thread. Then there's kernel level threads. Kernel level threads are what we're going to be using in class, and they are seen by the OS, and they're scheduled just like processes. So they're kind of separated in the OS's eyes from different from the other threads and the other processes that created them in the first place. They are scheduled just like other processes, so they will be subject to the same scheduling policies that we discussed before. As you saw in the too much milk example, threads can create race conditions, which is where synchronization comes in, which is our first main idea that we have for the class that we need to be able to prepare for. So really understand threads and really study them so you understand what they do, so you aren't confused when we get into synchronization. I think that's everything for today. As I said, I was very busy with the project, so it's very likely that I forgot something. If I did, please tell me so that we can all review the best we can. Thank you so much for watching. Bye.